Phase 1. The Soft Gripping Testbed. The soft gripping testbed will facilitate experiments in the design and control of soft grippers. It uses a parallel robot configuration, with a gripper motor, to emulate quadcopter trajectories on the 2D plane. The end effector moves at a velocity of 1.5 meters per second. The motor torques required to achieve this speed were determined by dynamic simulation. Especially in high-performance robotics, it is tempting to fine-tune the parameters in simulation to obtain a fragile controller that does not work in the real world. The soft gripping testbed ensures the robustness of our experiments in simulation. Phase 2. Aerial Swooping. We use two flying platforms, an omnicopter and a VTOL aircraft. The soft gripper is mounted on the underside of the platform. The flying vehicle swoops down to pick up the object, just like an eagle swoops down to pick up its prey. Phase 3. Catching on the fly. The flying platform gracefully catches a ball that is thrown into the air. But the story does not end here. The soft gripping testbed is not limited to aerial grasping. It is part of a much bigger picture. The map is divided into two segments. The upper half explores the research areas, while the lower half indicates the project outcomes. We will explore the design challenges first. Pneumatic grippers allow very fast grasping and comply to fit the object. Typically, they are powered by industrial air compressors. However, such heavy equipment is not suitable for the flying platform. We require a micro-pneumatic actuator. For instance, high-speed linear motors from Faulhaber provide speeds of 3 meters per second, with nanometer precision, while being compact enough to be mounted on the flying platform. It can be used to actuate a custom-machined, pneumatic cylinder, at a force of 3.6 newtons. Pre-inflated links can reduce the volume of compressed air required, and increase the grasping speed. An alternative is to use tendon-actuated or cable-driven grippers. Unlike pneumatic grippers, they do not require bulky compressors and can be directly actuated by motors. However, attaining sufficient grasping force at high speeds is a challenge. We can always look into nature for inspiration. Bones, in the claw of an eagle, provide high grasping force during agile maneuvers. Carbon fiber reinforcements embedded in the gripper can provide a similar function. In addition, differentiable simulators can be used to optimize for physical properties, including mass and strength. A central challenge in soft robotics is system identification. Finite element methods can capture the nonlinear deformation, but are computationally intractable. Model order reduction can drastically increase the computational efficiency, while still retaining the key properties. Once we have a tractable model, modern control techniques can be coupled with learning-based methods to develop novel control architectures. While motion capture provides accurate state information in the lab environment, real-world applications that demand precision require robust pose estimation. For instance, flex sensors embedded in the gripper can be used to measure the amount of bending. Recent advances in computer vision allow fast perception for robots. Event-based cameras can be leveraged for robust vision-based grasping. Research along these lines offers compelling demos, industrial applications and projects at the intersection of the two. The flying gripper is a soft robot gripper, attached to a quadcopter or VTOL aircraft. The flying platform swoops down to pick up the object, just like an eagle swoops down to pick up its prey. Thomas et al. Have achieved high-speed aerial grasping using a rigid gripper. However, their approach is not robust, since the object needs to be suspended in a particular configuration. Fishman et al. Have demonstrated a flying gripper in simulation, but they focus on pick-and-place applications, rather than aerial swooping. Another demo of interest is perching. The flying platform attaches itself to an object high up, such as a tree branch, using the same soft gripper. Fishman et al. Have also shown aerial perching using a soft gripper, but the approach has not been validated in the real world. On the side of commercial applications, we focus on robust grasping. The compliant behavior of the soft gripper allows for uncertainties in the position of the object. Likewise, the ability to pick up vibrating objects would be useful. Another feature of interest is ultra-fast grasping, closing the gripper within 100 milliseconds. McLaren et al. Have demonstrated such a high-speed gripper. The gripper is robust with respect to the object geometry, but the object needs to be thrown perfectly into the centroid of the gripper. Finally, let us explore the project at the intersection of the two, catching on the fly. Bresciani et al. And others have already demonstrated catching using a flying platform. However, they used a passive net or basket to intercept the object. During downward motion, we aim to develop an active gripper that can intercept the object during the upward throw. One of the main advantages of the soft gripping testbed is that several teams can work in parallel. For instance, the control team for aerial swooping can use a conventional air compressor for the pneumatic gripper, while the design team can simultaneously work on the micro-pneumatic actuator. Meanwhile, a separate team could be working on the industrial applications or vision-based grasping. There is something for everyone.